Hi, I'm Steve Marino. I'm the manager of the RARAF, the Radiological Research Accelerator Facility of Columbia University here at Nevis Laboratories. I'm going to give you a tour of the Microbeam facility, but first, a brief history of the accelerator facility. The history of RARAF traces back to Brookhaven National Laboratory in the 1950s. In 1950, the Cosmotron was commissioned at Brookhaven National Laboratory as the first GeV particle accelerator in the world. A 4 MV Van de Graaff was used to inject protons into the cyclotron. In 1967, the Cosmotron was decommissioned, and the Van de Graaff became the basis for the Radiological Research Accelerator Facility. At Brookhaven National Laboratory, RARAF produced monoenergetic neutrons and broad beams of charged particles for radiobiology and radiological physics. In 1980, RARAF was relocated to the Nevis Laboratories of Columbia University under the directorship of Dr. Harold H. Rossi, where it continued the work that had begun at Brookhaven National Laboratory. In the late 1980s, there was a national concern over the exposure of the general public to radon. This created a scientific need for the investigation of the effect of a single alpha particle at the cellular level. In response to this need, under the leadership of Dr. Eric Hall, the RARAF staff designed and built a microbeam facility that could deliver a single alpha particle to a cell nucleus. In 1992, RARAF was one of the first microbeam facilities in the world for radiobiology. During the mid-1990s, seminal work on the nuclear and cytoplasmic effects of alpha particles was conducted by RARAF scientists, particularly Drs. Eric Hall, Charles Geard, Tom Hay, and Richard Miller. Since 1995, under the leadership of Dr. David Brenner, further development of the microbeam facility has resulted in a beam diameter of less than 1 micron and a significant reduction in the time required to irradiate a cell. Currently, the microbeam facility can be used not only to irradiate a single layer of cells, but also complex three-dimensional biological systems. Therefore, research at RARAF can address scientific questions from the molecular level up to the tissue level. Interestingly, in order to study the effects of radiation on a microscopic scale, we need to use very large machines. In our case, particle accelerator. What is a particle accelerator? A particle accelerator consists of two parts, the accelerator itself and a transport system. The accelerator has an ion source to produce ions such as protons, and an acceleration system that uses an electrostatic charge to impart energy to these ions. The ions are then put into the transport system, which consists of a pipe through which the particles pass and magnets that are used to focus and bend the beam to the scientific workstation.